Okay, here I'm going to explain the formation of a simple single covalent bond. So I'm going to use the example of a hydrogen. Hydrogen have a single outermost electron because hydrogen is in the group 1 of the periodic table. But we know that for an atom to achieve stability, it needs to achieve 2 electrons in the outermost shell, in the first shell for hydrogen, and 8 electrons in the outermost shell for the remaining of the elements in the periodic table. In this case, since the hydrogen only have 1 outermost electron, it can share with the other hydrogen atom to achieve 2 outermost. So the single electron in the hydrogen can be shared with another electron, another atom, and the same electron from another atom can also be shared with the first atom. So in this case, we will have a sharing of a single electrons, and we shall draw it this way: 1 cross and 1 dot. And when we have a pair of electrons being shared, we call it a single covalent bond. Now we shall go to the more complicated example of a nitrogen. A nitrogen has an atomic number of 7. So that means it will have 5 outermost electrons. The criteria to achieve stability is still the same, which is to achieve 8 electrons in the outermost shell. So how can the electrons be shared among 2 nitrogen atoms? So let's do a trial and error. If each atom is to share only 1 electron, then what do we have? We will have 1, 2, 3, 4, 5, with a cross electron from the other atom being shared. So on the right, I will have 1, 2, 3, and 4. So you can see that in one atom alone, you will have 6 outermost electrons: 1, 2, 3, 4, 5, 6, which has not achieved the stable configuration. So sharing 1 electron is not enough. So let's try another example. Instead of sharing 1, now it shall share 2. Right, so going here, it share this, and same for this, it will share this. So now I will have 2 pairs of sharing: 1, 2, 3, 4. Right, 2 pairs of electrons being shared. Okay, so taking 2 out, I still have 3 remaining here that's not being shared. So let's count again for each atom. I have 1, 2, 3, 4, 5, 6, 7. So 7 electrons in the outermost, still not stable. Let's do another. Let's repeat one more time for the sharing. So if these were to share one more of the electrons with each other, so now I will have 3 pairs. Okay, so with 3 electrons being shared from the left atom, so now I should only left with 2 atoms, right? And that same goes for the nitrogen atom on the right. So now let's count the number of electrons: 1, 2, 3, 4, 5, 6, 7, 8. Great. So you can see that by sharing 3 electrons from each nitrogen atoms, we can achieve the stable configuration for each nitrogen atom. And in this case, since they are sharing 3 electrons each, so we will have 3 covalent bonds between the 2 nitrogen atoms. So this is one example of a triple covalent bond. Let's go for one more example. Let's try C2H4. So carbon has an atomic number of 6, hydrogen 1. So I have carbon and a carbon here. So 1, 2, 3, 4. 1, 2, 3, 4. So we can see that to achieve stability, it should share some electrons, right? Well, there's a few ways to do it. I could share 4 electrons from each of the carbon so that I have a C2. However, if I were to do that, I would have achieved something like this: 1, 2, 3, 4, 5, 6, 7, 8. Carbon, carbon. So I will have a carbon, this quadruple bond, and that will leave this molecule with no extra spaces for the hydrogen atom. So this particular configuration is not the one that can be found in the C2H4 molecule. So let's go for something less. Instead of sharing 4 electrons, now let's try sharing just 2. 1, 2, 3, 4. So that means on the left, I will have 2 more electrons left for the hydrogen. The same thing goes for the right atom. And we can see that for hydrogen, it just requires 1 electron. And well, I'm going to put it here in this way. So we can see that these 2 electrons from the carbon could go to each of these hydrogen atoms. There should also be 2 hydrogen atoms, and each of these hydrogen atoms need 1 more electron. So this electron will come here, okay, and this electron can be shared here, right? And same thing goes for this and this. So if we focus on the left, we will see that the carbon will have a pair of covalent bonds being shared with the other carbon atoms, and for the hydrogen, it will share a single covalent bond each. And due to symmetry, the same thing can be said for the right side. So we can see now that for the carbon atom on the left, I have 1, 2, 3, 4, 5, 6, 7, 8. So it achieved 8 electrons in the outermost shell, and the same thing goes for this carbon atom, and also each of the hydrogen, they also achieve a stable configuration of 2 electrons in the outermost shell, or in their first shell, right? So this would be the electronic configuration of the C2H4 molecule, right? So can you try the remaining 2 molecules, which are CH3OH and CO2? Right, thank you.